Hey everyone, and welcome to our lesson on solving trig equations. And this is going to involve factoring, and really that's in kind of two different forms. So one being kind of factoring out a greatest common factor from an expression, and then the other being factoring as if it were a quadratic. So we're going to take a look at kind of both variations here, do a couple sample problems, and then there is kind of a subset for you to do as well to practice. So in our first problem here, generally I'd be trying to isolate cosine of x, but I run into the situation that cosine squared x and cosine x can't really be separated from one another. And for this, generally I would use kind of a process that is called U substitution, in which I say, okay, well, if that cosine of x is just a little bit tricky for me to wrap my head around solving, if I write that as just u, then this problem can then be written as u squared minus u minus 2 equals 0. And this is a quadratic that I can easily factor. Again, no different from the first statement. It's just it looks easier because it's closer to, x squared minus x minus 2 equals 0, which is a quadratic that I can factor. So whenever I'm doing U substitution, while it always kind of feels a little bit quirky, it's meant to just make the problem a little bit more visually appealing so that you can then identify exactly how this needs to be factored. So in this case, I can break this off into u minus 2 and then u plus 1 equals 0. So that is with factoring a quadratic. And then once I've done the tricky part, I can plug my cosine of x's back in. Okay, so I end up with these two different equations. And with factoring, what we say is, okay, well, if that equation on the left ever equals 0, then that's going to be an answer. Or if the equation on the right ever equals 0, that's going to be an answer. So if I take a look on the left here, I have cosine of x minus 2 equals 0. That would lead me to cosine of x equals 2. And if you look around your unit circle, or if you understand that cosine only ranges from -1 to 1, right on your graph, there's no x value that I can plug into here to get this. So from here, we end up actually getting no solutions from that particular factor. Our other factor that we have is cosine of x plus 1 equals 0. Take away 1 from both sides, I end up with cosine of x equals -1. And now I'm looking for, where on my unit circle is my x coordinate, because x is for adjacent, -1. And I can find that at x equals pi. So if I'm only reporting out on solutions in between 0 and 2 pi, that would be my answer. So yeah, those are all the solutions. Second problem, 2 sine of x cosine x equals cosine x. We don't actually want to divide by cosine x here, and that's because whenever you divide by something like that, you're actually removing a potential solution from your problem. And I'll probably talk about that more in class. But in this particular case, and on this, in these sample problems, we're going to be looking to set one side of our equation equal to 0, and then factor the left-hand side of my equation. So on the left-hand side of my equation, what's common between the two terms that I see there? Well, that's going to be cosine of x is common between those two. So if I factor out a cosine x from both of those little mini expressions, I end up with 2 sine x minus 1 equals 0. So if you kind of need help with that step, I might look in reverse and notice that, if I were to distribute that cosine of x, I would arrive at that expression that I have up top. And that kind of, lends some credibility to what we had just done. But now if you look, I have two different factors. When multiplied together give me 0. So I can again set each one equal to 0 and then try to solve these to figure out what I get. So the left-hand side, I'm just curious as to, on cosine of x, so when does the x coordinate equal 0 on the unit circle is what that question on the left is going to equal. So from here, I would end up getting solutions of x equals pi over 2 and also 3 pi over 2. And I'm going to keep this little solution set open and then just try solving this equation on the right, which is 2 sine x minus 1 equals 0. So I'm adding 1 to both sides. Then I'm also going to divide by 2. So I end up with sine of x equals a half. And sine being my y-coordinate, looking on the unit circle for where that's going to be a half, I'm just trying to visualize this. So we end up with these angles here. So that looks like pi over 6 and 5 pi over 6. So pi over 6 and 5 pi over 6. So all four of those ends up being solutions to this problem. I did say at the beginning of this that if you divided by cosine of x from both sides, you would remove solutions. So you can go ahead and kind of do that, but you'll notice that you're going to miss out on pi over 2 and 3 pi over 2 should you do that. So that's just kind of important to recognize. So our next one is going to be back to kind of the quadratic factoring. And you'll see I had kind of pre-worked some of this. So I did some u substitution here. So I replaced sine of x with u, okay, just so that it was a little bit visually easier to see. And then I also did a little bit of solving here. So if you replace all your u's with, or replace all your sine of x's with u's, try to get everything on one side and 0 on the other, then we end up needing to factor this quadratic, which was relatively straightforward, becomes 2u plus 1 times u plus 1, and then I am replacing my u's with sine of x, and I end up with this statement here. Just keep my right hand side, and then I'm going to break this into two separate equations that I have to solve. So when does that equal 0, and when does, let's see, I need a plus 1, and then when does that equal 0? So if I kind of solve this a little bit further, so this is going to be negative 1/2 here, and this is going to be sine of x equals negative 1. So I'm looking for y-coordinates that satisfy those equations on my unit circle. So negative 1/2, if I use this little unit circle potential drawing that I already have right here, I can go there, so that's going to be 7 pi over 6 and 11 pi over 6 for my negative 1/2. And then negative 1, so a y-coordinate of negative 1 is only going to exist at 3 pi over 2. So I end up with those solutions. Last problem, given the mix of tangent and sine, this is probably going to look like a factoring out greatest common factor. So I'm going to add 3 tan x to both sides, which is just going to combine with these. So I end up with tangent of x, sine of x, minus tangent of x equals 0. I see that tangent is common to both of those expressions. So I have tangent of x, I'm factoring that out of both of those. So I end up with sine of x minus 1 equals 0. Then I'm going to set both of these expressions equal to 0 and figure out if the unit circle can help me figure these out. So solving this a little bit further, that's sine of x equals 1 and tangent of x equals 0. So my solutions are going to be, so where does tangent equal 0 on the unit circle as I make a full rotation? Tangent is y over x, so if y is 0, then I should be good. So that's going to be at 0 and pi. It's also at 2 pi, but again, that's the same as 0, so I don't necessarily want to include it. And then sine of x equals 1. Sine is my y-coordinate, so that's going to be at pi over 2, where that equals 1. All right, so those are all of our solutions. We did 2 variations of factoring out a common factor, and then two variations where you're factoring a quadratic, and I did kind of show U substitution for that. So see if you can tackle these other problems here. So let's see, we've got just 4 problems, and that will be good demonstration. Thanks.